Thank you. Thanks for the introduction. And I would like to start by thanking the organizers for the invitation to speak here. It's a pleasure. It's the first time I'm in Brazil. So I'm going to talk about something that I think for this audience is going to be slightly exotic, I think. So let's see. So this is based on a few papers, these 4 papers here, that I wrote in collaboration with my long-term collaborators, Pablo Bueno, who's a postdoc in Barcelona, Robbie Henniger, who is a postdoc in Durham, Ángel Murcia, who is also a postdoc in Barcelona, and Aitor Vicente, who is my PhD student. And also I will mention some work in progress, okay? So this is the outline of the talk. So given this seminar several times, or this talk several times, I don't usually include an outline, but I'm going to do it here because I'm expecting several questions that I will address in the last part of the talk, in particular regarding stability issues, okay, of the regular black holes, both at the level of the inner horizon. You'll see that regular black holes have inner horizons. At the level of the going beyond spherical symmetry, because I will be discussing spherical symmetric black holes, and at the level of the theories themselves, okay? So I will address this in the final section, okay? So what I will do is I will make a few general comments about what regular black holes are supposed to be, and how people have struggled to actually come up with actual theories in which these things appear as solutions, okay? I will tell you a mechanism in which regular black holes actually arise as the unique spherically symmetric solutions of certain theories that correct the Einstein-Hilbert action by an infinite towers of higher derivative corrections. All these theories satisfy a Birkhoff theorem, so they're actually the unique solutions in those theories. And the fact that they satisfy a Birkhoff theorem actually allows us to study dynamical formation. So I will show you, I think, the first examples of a theory which you can actually evolve a thin shell or a star and see how a regular black hole forms, okay? And then I will comment on, in particular, stability issues, and which is part of future directions and other things that we would like to do, okay, with this. Okay, so let me start by saying a few things about regular black holes. Well, as we all know, space-time singularities are a generic prediction of general relativity. So they form under general circumstances through collapse, for example, and they are expected to happen also at the beginning of the universe. And it's something that, well, in particular, they occur in the interior of black holes. This is expected to be an artifact of an incomplete description. These singularities, the fact that they are generic, means that they cannot be resolved within general relativity. You need something else. You need something that goes beyond general relativity, because in general relativity there are singularities. Okay, there are curvature singularities, and we expect that there are no physical quantities that are infinite. In particular, well, tidal forces and things like that should not be infinite, no? Right. So okay. So it's a fundamental question: how do they get resolved? No, how do we resolve singularities? So there are 2 possibilities, not necessarily mutually exclusive. So there may be perhaps frameworks in which the 2 are like compatible with each other, or it's partially true, one of the 2, and so on. So first of all, it's possible that you need a fully quantum description. So perhaps near singularities, we cannot use the metric to describe the fundamental degrees of freedom of gravity. So in that case, then, well, what I'm going to tell you wouldn't be sensible, perhaps. And possibility 2 is that they can actually be resolved within a regime in which the classical metric description is valid, okay? And this is actually the realm of this community of people who study regular black holes, and not only regular black holes, but other things, like, for example, you've heard about other black hole mimickers that don't have necessarily horizons, but they may have, for example, light rings, unstable light rings. So looking at them from very far away, you wouldn't distinguish them. So they're very similar to black holes, but not necessarily black holes, okay? Okay, so what are regular black holes? Well, regular black holes are black holes with no singularities, okay? So all the curvature invariants remain finite. And this is actually a field that is very, very old. So this started, I guess, in the 60s of last century with Sakharov, Bardeen, and others, in which people proposed models in which literally they took a metric, they deformed it in a way such that the singularities disappear, okay? So, well, in particular, these are not actual general relativity solutions, because in general relativity, black holes have singularities, no, as I said. So what people did originally was to postulate them as theoretical testbeds and see what happens. I mean, what would change if instead of having a singular black hole, you had a regular black hole? I mean, what would be the differences in whatever physical quantities you may be interested? But of course, in the absence of a dynamical framework, all these ideas are very poorly justified. I mean, of course, you can write whatever metric you want, but if it's not a solution to something, then, well, it's not very clear whether this means anything at all, not related to physics. So, well, let me give you an example of this, okay, of a regular black hole. So this is the sometimes called Hayward black hole. Perhaps it should be called Poisson Israel because it appeared actually originally in a paper from the 60s before Hayward wrote his actually pretty famous paper 20 years ago about this. So the metric is static and spherically symmetric. It only has one function that characterizes it, just like Schwarzschild. And the blackening factor takes this form. So it's very similar to Schwarzschild, but there is a parameter here that deforms the usual Schwarzschild solution, this alpha here. And well, of course, if you go to long distances, well, you see that this behaves like the Schwarzschild or Schwarzschild-Tangerlin solution. But if you go in the inside where you have the, well, divergent curvature invariance, it turns out that this has a sort of de Sitter core. The de Sitter length is actually determined by this parameter. And well, there's no singularity. Okay, the singularity is gone. Okay, so this is perhaps the simplest possible modification of Schwarzschild that leads to a regular black hole. Okay. Okay. So well, yes, this is what I just said. So there's actually a huge body of literature about regular black holes and trying to embed them in theories, in particular theories of nonlinear electrodynamics coupled to general relativity. So let me mention that. So in that context, you can actually obtain them as particular solutions to general relativity coupled to theories like this, for example. So you have Einstein gravity and you have some very complicated Lagrangian that depends on the Faraday tensor in this, well, very bizarre way. And this thing has several problems. First of all, regular black holes in these theories are not the generic solution. So you have singular solutions as well. So you actually find regular black holes in very particular points of the space of solutions. You actually need to fine-tune the coupling of the theory with actually the integration constants, and this sigma is actually proportional to the alpha that I showed you before. Okay, so at very peculiar points in the space of parameter, you get a regular black hole. Otherwise, the black holes are singular. Okay, in particular, Schwarzschild is also a solution of this. So, well, first of all, you need highly ad hoc matter. Well, as is clear from this. In particular, this doesn't have a Maxwellian limit, or if you, well, even if it had it, the solution wouldn't be regular. Okay, so only in very peculiar situations you get a regular black hole. It requires a fine-tuning of parameters, also actually a pretty bizarre way, kind of fine-tuning. And this is what I just said. So regular black holes are not the general solutions of these theories. Okay. So let me back up a little bit and say a few things. So general considerations. So, well, as I said before, singularity should be cured by some modification of Einstein gravity. No, so far, I think we agree on this. Everybody will agree on this. And so we may think of string theory, for example. What would string theory predict regarding corrections to general relativity? So we have different kinds of corrections, in particular stringy corrections and quantum corrections. No? So, well, one thing that string theory predicts is that we have infinite towers of higher curvature corrections that appear weighted by powers of alpha prime. No? It's like related to the fact that strings are they have finite size. It's not a field theory. No. And then we have quantum corrections, okay? That's something else. I'm going to be thinking all the time that the thing I'm going to do is motivated by this kind of thing. Like in string theory, you have infinite towers of alpha prime corrections. I'm going to do something motivated by that, not that, okay? Because that's very difficult to do. So perhaps these effects would be enough to resolve singularities in some cases, if we were able to include the whole thing, without taking into account quantum corrections, but we don't know how to do that. So we're going to do something else, okay? So what we are going to do, and this is where I start telling you about my results, is to consider a bottom-up setup. Instead of top-down, we consider a general gravitational effective action, if you want, but we're going to select the basis of the effective action in a very particular way, okay? So we're going to select it such that we can actually control the effects of this infinite tower of terms, okay? And you will see that the result of this, so we're going to resum the terms, okay? That's something rather peculiar, okay, because it's not an effective field theory, because we're going to consider the couplings not perturbatively, we're going to go beyond perturbative order. So everything I say will capture the most general perturbative corrections, but I'm going to do something else. I'm actually going to resum the full series, okay, and see what happens. And what will happen is that you get actually a generic resolution of the Schwarzschild singularity, and we'll do this in spherical symmetry. And for these theories in which you have an infinite tower of terms correcting Einstein-Hilbert, you will actually have an infinite number of free parameters that will appear there. I will fix all of them proportional to a single parameter that will be, if you want, related to what will be alpha prime. Okay, will be like, I will call it alpha, will appear somewhere. So you could also fix it to the Planck length, for example, but I will choose to take two different scales. Okay, one for these corrections and one for G Newton. And then, so I will show that, well, this theory satisfies a Virchow theorem. So actually, by imposing spherical symmetry, you get a staticity. So that allows us to actually do dynamics. So we can actually take a shell of matter. I will show you briefly the case of a shell of matter and also a star, and see what happens with collapse. We'll see that collapse leads to the formation of regular black holes and some bizarre stuff that happens inside the black holes, you know, and then what happens with the shells and the stars and so on. And then I will comment on how much we can trust that picture, but okay, at least we'll be able to produce a model of dynamical formation, okay, of these things. So for that I have to tell you what class of theories or what kind of terms I'm going to consider in the action, okay, and these are called, for unfortunate historical reasons, they are called quasi-topological gravities. I'll tell you a little bit more about that in a moment, why they're called like that. So these are L of Riemann theories of gravity, okay, so the kind of things that you would expect in an effective action of gravity. They can also include the covariant derivatives, but I will not include them here. That's a bit trickier, so I will just do it with polynomial densities. And this is the way they are defined. So as you know, Lovelock's theorem tells you that the most general theories that have second order equations, which are covariantly conserved, are Lovelock gravities. No? So I'm going to consider a broader class of theories, okay, that in general have fourth order equations, but they happen to have second order equations in the case of static and spherically symmetric backgrounds. Okay, this is what a quasi-topological theory is. So in particular, Lovelock are particular cases of these kind of models. So if you look at what theories satisfy this, so in particular in 4 dimensions, only general relativity satisfies this criterion. But that's not the case in higher dimensions. So in 5 or more, you have actually densities at every order. I think this came as a surprise to several people. This was discovered almost at the same time by Julio Oliva and Ray, and by Rob Myers and Robinson, the cubic case. And they were looking at different things. So Julio and Ray were looking for theories that satisfied a Virchow theorem, higher curator theories satisfied a Virchow theorem. And Myers and Robinson were looking for holographic theories whose duals in 4 dimensions had A and C, the trace anomaly coefficients, different from each other. So that's different from Lovelock. Okay, so they were looking for some nice models that would do that. And they came up with this, they found these quasi-topological theories. In particular, Myers and Robinson were a bit confused because they found a theory in 5 dimensions which was cubic. It was not a Lovelock theory, but it looked a lot like a Lovelock theory, so they thought maybe we found a new topological invariant in a particular dimension, just like it happens for Lovelock theories. It was not the case, so they tested it. It was understood later that was not the case, but that's why they call them quasi-topological. They are not quasi-topological in any sense, okay, but they look like something that in particular dimensions is topological, which are Lovelock theories, okay? But anyway, so that's why it's called like that. And then, well, people extended this to quartic orders, quintic orders, and then finally to every order and in general dimensions. So to show you a little bit what they look like, let me do that. So it's convenient to write everything in terms of the Weil tensor and the traceless part of the Ricci tensor. And then the first linear, quadratic, cubic, and quartic order, they look like this. Actually, well, this is Einstein-Hilbert, of course. The second piece is actually the Gauss-Bonnet density, written in a funny way. So for those of you who know this is just the usual Gauss-Bonnet term. But this, for example, is no longer the cubic density, okay, of Lovelock. It's something else. It's something more general. So for example, in 5 dimensions, it's non-trivial. So Lovelock would be trivial cubic Lovelock would be trivial in 5 dimensions. So this is the quartic, and you may be wondering why I'm showing you so many of this. This is the quintic. As you see, this is a mess, no? But actually, what happens is that you can actually show that you can construct them recursively. So if you have the first 5 densities, you can show that a density defined by this recursive formula, it's also a quasi-topological theory. So you can actually show that you can build them at arbitrarily high orders. And there is degeneracy in the sense that at every order are several possible quasi-topological theories. So we'll choose a representative at every order, but in principle, you could choose others, okay? Actually, there's an explicit formula by Javier, who's somewhere here, and Angel Murcia, where they actually give you the explicit formula at every order in every dimension, which is a mess, but okay, that's not relevant for us. So one may think this is very restrictive, but actually it's not that restrictive in the following sense. So imagine you take any gravitational effective action that you want, like this, with some arbitrary couplings and whatever powers of curvature you want. As long as you remain with perturbative couplings, so that is beta, you consider just them to be like order 1 in beta, so just consider that they're small. Then there's always a field redefinition that you can do in the metric that you can map, so that you can map the original theory into a quasi-topological theory, okay? So there's an example, for example, in one paper in which we do this for the leading correction of type 2A string theory in ADS5. You see the leading term is on bile to the fourth, for example. It's a complicated thing. You can actually do the mapping and see that all the relevant physical quantities are the same in both frames, okay? So everything I'm going to say is such that it captures the most general perturbative effects arising from any gravitational action. But I'm going to do something else. I'm going to go beyond the perturbative regime. So I'm going to do something unusual and weird, okay, in some sense. I'm going to try to resum the series in a particular basis. Okay, that's what I'm going to do. Yes, sure. Yes. As long as you remain at perturbative order,
Too late, yeah.
It's fine. So these degrees of freedom are... What happened, sorry? It's okay? Yeah, you're right, but that would be relevant if I cared about these couplings being finite. As long as I remain perturbative in the couplings, that's not important. Those degrees of freedom play no role. So that's fine, okay? Yeah. Okay, so let me tell you now about what happens with how the solutions come about. So let's consider a general spherically symmetric ansatz. So this is a general spherically symmetric ansatz. It depends on the time and R. It has two functions, okay? Okay, so now I'm going to consider one of these theories, okay? So there are infinitely many, well, infinitely no, I'm going to actually truncate the series to some curvature order that I'm going to call n max, and then I will take the limit at some point. So imagine I have this, so these couplings are all free parameters. I'm not fixing them, I will not fix them at any point, so they are all, I have n max minus 1 actually arbitrary couplings. And all these densities, okay, that have this property. Okay, so if you take the equations of motion of these things and you plug these ansatz into them, well, you get two conditions that are highly non-trivial, especially for theories like this. First of all, you see that the n coordinate does not depend on R, okay, and the n function, and the f function does not depend on t. So very quickly you see that this implies, well, that n is exclusively a function of time, which means that you can reabsorb it in a redefinition of time because it only appears here. So you can set to 1 so that it's going to be asymptotically flat, the solution. And f, it only depends on R. Okay, so that's essentially Virchow's theorem. Okay, so well, that's precisely what happens. So these theories satisfy a Virchow theorem, which means that every spherically symmetric vacuum solution is also static. So this is actually the original motivation of Olive and Ray. We have proved this for arbitrary orders. And there's actually something more interesting, more powerful that you can prove that will be published soon, which is that you can also prove the other implication. So if you consider some higher curvature theory and you ask, okay, what happens if it satisfies a Virchow theorem? Well, what happens is that if it satisfies a Virchow theorem, then it is quasi-topological. So we prove quasi-topological implies Virchow, and Virchow implies quasi-topological. So any higher curvature theory that has a Virchow theorem is of this class. Okay. Okay. There's an extra equation that we have to satisfy, which is the equation that determines what is the solution. Okay. So the equation is this. It's a first order equation, differential equation that you can integrate once, just like for instant gravity, and you can write it down in terms of the, well, something that you can identify very quickly as something proportional to the ADM mass. And for those of you familiar with Lovelock theories, this is literally the same equation that appears in Lovelock gravity, and the only difference is that here, n max is not truncated at the order that is truncated in Lovelock gravities, which would be the, I guess, the sailing function of d minus 1 over 2. Well, here we can have densities of arbitrary orders, and that will make a difference for this, for what happens in the interior, okay? Okay, so this is a very simple equation. So it's an algebraic equation for f, so you can try to solve it, well, numerically after n equals 3, I guess. Well, you have to be a bit careful with what qualitatively impose on the couplings, because otherwise you can have more things, but okay, we'll explain that later. So let's go case by case. So the simplest case is, of course, instant gravity, no? For instant gravity, all these couplings are 0, and then, well, we get Schwarzschild, no? Schwarzschild black hole in d dimensions. So consider now a quasi-topological theory with a finite number of corrections. Well, in that case, I'm just truncating at some n max, and what happens is that there is a singularity still. So if you compute the curvature invariance, you will see that it is still singular, but it's weaker. So this is what happens in Lovelock, for example. So the curvature invariance, I mean, the thing is still singular, but it's weaker than before. And you see here there is a dependence or nmax that appears here. But actually, it's interesting because you see that this is 2 minus d minus 1 over nmax, and then what happens is that the exponent tends to 2 as nmax goes to infinity. And this is precisely the form that you require in order to have a de Sitter core, which would correspond to a regular solution, okay? So, well, that's precisely what happens. So if I consider now an infinite number of terms in the series, well, this is what happens precisely. No? There is a de Sitter core, the singularity is gone. You can compute all the curvature invariants for whatever model you want, because I'm not fixing the alphas, okay? And well, the singularity is gone. There are some qualitative requirements that you need to impose on the alpha, on these alpha n's here. So this is an example of a sufficient condition. It's not necessary. You can have some of them being negative, but it's just to make it simple. So if you keep all of them positive, okay, or 0, you can set some of them to 0, doesn't matter. And you make them reasonable in the sense that this alpha n has dimensions of length to the 2n minus 2, I think. So if I do 1 over n, this is just telling you that the coefficients are order 1, essentially, of the different terms in the dimensionless coefficients in front of each term are order 1. Okay, so it's a very reasonable assumption. Well, if that happens, then you have a regular black hole. Let me give you an example. It's a very particular case, and I will be talking about it all the time just to simplify the discussion, because, as I say, there are infinitely many possibilities. You have the alpha n's are free. You can choose them however you want, as long as, for example, this condition is met, then you will have a regular black hole for this theory, okay? So this is an example. This is this choice, okay? So I'm setting all the alpha n's to be proportional to a single alpha to some power. So you can imagine this is something like playing the role of alpha prime, okay, here. This thing here is just a technical subtlety. You can forget about this, for example, in 5 dimensions, which is the case that I'm going to show you the plots about. So this is just some number in 5 dimensions. And in that case, you actually recover the Hayward black hole. So the Hayward black hole is actually a solution of our theories for a particular selection of the couplings, okay?
Pablo, well, here, in the back.
Yes.
I stole the microphone. Can you go back 2 slides, please? Because it is, okay, yes, from there it is clear that if you take n max to infinity, then you fall into R squared. But you don't really need that, right? For a fixed dimension, if you go high enough in n, as long as that doesn't beat the 2, you still get something regular.
No, but it's not. But it's still singular. So I will actually show you that precisely. So here I have a plot. So this is actually, so this is the blackening factor for instant gravity. So this is just well, the usual Newton potential. It goes 1 over R to the d minus 3. And this is when you add n max equals 2, n max equals 3, n max equals 5, n max equals 7, I think, and this is n max equals infinity. It doesn't seem to change much, but if you plot the Kretschmann invariant, you see that it's only when you include the infinite tower of terms that it is regular.
So okay, thank you.
You can check other invariants, but in spherical symmetry, they are all essentially, I mean, if the Kretschmann invariant is finite, then all of them are all the possible invariants are finite, okay?
Thanks.
Actually, depending on the values of the, so now everything, so this is characterized by a mass, so there's a mass of the solution, which is related to the integration constant, there is the alpha parameter, no? Depending on the values of the mass, you can have different possibilities. So this is the Schwarzschild case, so there's alpha equals 0, so this is the usual thing. The one that I show you is when alpha is positive, and there is some critical mass, so there's some relation between the mass and alpha such that, well, what happens when they are equal is that you get a extremal solution, so this would be a regular extremal black hole. This is a non-extremal regular black hole. It's the one I showed you before. It has 2 horizons. You have the outer horizon, the inner horizon, but I will comment about its properties later. And there is another situation, so this is a bit different from the usual case in which you have charge, for example, because the extremal case does not separate non-extremal solutions from naked singularities. It separates non-extremal solutions from completely regular horizonless geometries which are non-trivial. Okay, so it's something else. Okay, so this would be an example of, yes? Yes?
How is that? So
no, Virchow theorem means that if you impose spherical symmetry, you have a staticity implied. That's what Virchow theorem means.
Nothing more than that. Okay.
Yes. Okay. Because the extra thing would be that the function is the same as in general relativity, but that's the thing that changes. Otherwise, it will be trivial, no? Okay. So before saying things about collapse, let me make a comment about something called Markov's limiting curvature hypothesis, which is something that I find a bit funny. And it's a statement that it's a proposal by Markov from, I guess, the 60s or something like that, which is the conjecture that there is a universal upper bound on a space-time curvature. Okay, so imagine you compute all the curvature invariants, for example, the Kreisman invariant, and the idea of Markov is that there is some fundamental limit on how large the curvature can be. So for example here, well, in his proposal, the relevant scale is the Planck length, so this would be some number divided by the Planck length to the 4th power. Okay, that would be what he would claim. Okay, so this is an idea that was proposed at some point, but actually in our context, this would mean something precisely. And what it would mean is that if I fix the alpha n, so I consider a particular theory, there should exist some maximum value of the curvature which cannot be surpassed. And you would say, well, that's obvious because the solutions are regular, so that will happen. But it should be independent of the mass of the solutions. So regardless of which mass I'm considering, there should be like a fixed cutoff maximum value of the curvature. And actually, we observed this actually like in some examples. So you see this is for different masses in some example, and you see that it is actually, it cuts off regardless of the mass. And there was some proof of this for our models in this paper that appeared later. And it turns out that, well, there is some scaling property that happens for our solutions that doesn't happen for all possible regular black hole models. So this is actually, well, an interesting feature. I wanted to mention this in case you didn't know it. Okay, so we have a framework in which, under rather generic conditions, all the spherically symmetric solutions of this theory of Einstein gravity coupled to infinitely many terms of corrections with arbitrary couplings, well, they generalize the Schwarzschild black hole, but they are regular. Okay, so they are regular solutions. I said before that so these satisfy a Birkhoff theorem, so we can actually ask about what is the dynamics. So in the spherically symmetric sector, we have something that collapses. What happens? What is going to happen? Does it form a regular black hole, or what's going on? So that's what I'm going to address now. Okay, so that's the third part of the talk. So the simplest possible model, and then there are all kinds of questions one can ask. For example, I'm including higher curvature terms at the level of the metric, but I'm not going to include higher curvature terms at the level of the stress tensor, for example. So that's a reasonable complaint one can make. But I'm just going to consider the simplest possible model, which is like a thin shell with this kind of stress tensor. Okay, so this is a very standard problem in general relativity. Okay. So, well, inside the shell, we have a flat space-time. Outside the shell, we have, because of Birkhoff theorem, we have our static and spherically symmetric solution. Okay. And what we want to find is what is the trajectory of the shell in the, well, the coordinate radius of the shell, no, as a function of the proper time of the shell. So there will be some evolution. But in order to address that, we actually need to find the Israel junction conditions for these theories, okay, which is a complicated problem. So in order to address that, what we did is the following. We actually took our theories and we dimensionally reduced them on the sphere, okay? And if you do that, which is a mess, I'm skipping a lot of, you can imagine a lot of calculations of what we actually did. You actually get a two-dimensional Ornetsky theory, okay? So you reduce to 2 dimensions, you get a Ornetsky theory that has second-order equations of motion, everything is well-defined, you can identify the boundary term, and from that, you can actually extract what is the second junction condition, which is the tricky one, okay? So, okay, the first junction condition, which is the same as in Einstein gravity, the continuity of the induced metric on the surface, at both sides of the surface, well, it imposes this. And once we have this piece, here we can actually compute the second junction condition that tells you that there is this discontinuity where this is the stress tensor on the boundary of the, sorry, on the shell, okay? Okay, if you do that, you get, well, first of all, something which is the same as in Einstein gravity, the proper mass of the shell is conserved, and you get an equation for the shell motion. This is some kind of integral differential equation. I mean, the details are not so important. You get the shell's proper mass, the space-time total mass that appears here in the integral, and everything depends on the metric function for whatever, well, in whatever theory you are doing this, no? And you have to solve for r of tau, okay? Okay, let's start with Einstein gravity again. So if you do this for Einstein gravity, it's a nice problem that you can try. It's not a geodesic, so it's something a bit trickier because there is energy momentum in the shell. But you can see that well, you have some energy conservation equation, and the potential is negative definite. Okay, so well, singularity is unavoidable. I will show you a plot in a moment. But if you do it for these theories, in which you have these infinitely many terms, well, what happens is that the potential, well, you can write it in the same form, but you cannot solve this explicitly, but you can see how it goes when you go very far away. It's like in Einstein gravity. But if you go near the r equals 0, again, you have the same thing that well, it doesn't diverge, but you get actually this kind of form here, okay? So there's a turning point, so the potential looks like this, okay? So now that we have this, we can actually see, well, what happens, we can actually integrate the equation. It's a first order differential equation, you can integrate, you give some initial conditions to the shell and see what happens, okay? So if you do that, well, you imagine you start with a shell at some finite radius that is larger than the would-be outer horizon. What happens is that it keeps on decreasing, I will show you a plot in a moment. It gives rise to a regular black hole as seen from the outside, okay? So it crosses the outer horizon. So it forms an inner horizon, and of course there may be issues with this. I will talk about those later. But okay, in this scenario, the inner horizon is just there. I mean, it forms the inner horizon, and then eventually it stops decreasing. So the size gets to a minimum point, and then it starts growing again. Okay. Well, that's more or less obvious from the potential plot that I showed you. It crosses the inner horizon from the inside, and actually it appears in a new universe through a white hole where it reaches its maximum size again, the original size again, and it starts doing this all the time. It's like a bouncing, sort of dynamical bouncing thin shell model. So I can show you the plot. So it does like this. So in instant gravity, this is very standard. You start with some size. It crosses the. Actually, it doesn't appear here, but okay, it crosses the size of whatever Schwarzschild black hole you have, and eventually, after a finite proper time, it just reaches zero size, so you get a singularity. No, in this case, you get that it crosses the outer horizon, the inner horizon, and always inside. It's actually here, but it's not visible. But it doesn't matter. It always happens inside the inner horizon. It bounces back, and then it crosses the inner horizon from the interior. So you actually get something like this. So you start from. So you can imagine that some civilization prepared this at some point, and then it starts collapsing. So it leaves behind an outer horizon, and there is the inner horizon. And then once it's in the inner horizon, you can actually extend it to another region here. Then it goes back, and then you create infinitely many universes. So it's similar to like Kerr or Reisner-Nordstrom black holes. Okay. Okay. I don't want to. How am I doing with time? 15 minutes, okay. So I will skip this quickly because this is another model, okay? It's just Oppenheimer-Snyder, but the ideas are the same. Well, what you consider here is a pressureless dust star. So it's a star instead of a shell. So you can see what happens in that case. In the inside, you have Friedman, Lemaitre, Robertson, Walker. In the outside, again, you have the spherical symmetric solution. You need to solve for the equations of the star surface. Well, you can do it, and actually what you find is that in this case it is actually a geodesic. Okay, it's like a geodesic in the background. So the surface radius, it's actually following literally like a radial geodesic. And actually that's the same equation that controls the Friedman equation. So if you consider cosmology in this model, is literally the same equation that controls the dynamics of the scale factor. Okay, that's a curiosity. It's the same as in instant gravity. So this thing that I work here is the same as in instant gravity. Obviously the equation is not the same because the metric function is different, but that's the only difference. Okay. And what you get is, well, essentially the same, okay, as before. So it's a star, it collapses for instant gravity. For this, it doesn't collapse. And the only difference here is that you have a density profile. And in this case, it reaches a maximum density, and then it goes down again, and so on. For instant gravity, it just diverges, okay? This is just, well, this is the usual Oppenheimer-Snyder context in which you can actually do this. There is no pressure. So this is a sort of a cold dark matter bouncing universe model, okay, because the student tensors would be like a cold dark matter. So you would like to have a full with all kinds of matter and so on, but that's more complicated to do. It cannot be done analytically even in instant gravity. But okay. So let me summarize before going to addressing some comments and future directions. So I told you that the Schwarzschild black hole singularity gets generically in the sense that you don't have to do any fine tuning of parameters in d greater or equal to 5 by the effect of infinite towers of higher curvature densities, which are general enough to control the most general effective gravitational action, as long as you remain perturbative in the couplings, but I'm doing something more general, no? As I said before. These black holes are actually the only vacuum spherically symmetric solutions of this theorem. Of these theories, there is a Virchow theorem that holds for them, and since there is a Virchow theorem, I can study dynamics within the spherically symmetric sector. Okay, that's what I did in a few cases, a few simple cases. And these represent, I think, the first fully dynamical models in which there are actually theories where there is collapse of matter leading to the formation of regular black holes. And I think this is a framework. I think the regular black holes community are like this a bit because this is a framework in which you can address many questions that people have only addressed very heuristically or with very approximate metrics or with probe fields and so on in a framework where you have the possibility of considering the actual dynamics, okay, of the models. So let me say a few comments. I think the first slide is about stability, okay, and there are several issues that we need to take into account regarding the stability of the horizons, the solutions, and the theories, okay? So the first is regarding the stability of the inner horizon. So the inner horizons in general are known to suffer something, well, suffer. There is something called mass inflation instability, which tells you that energy densities, if you perturb them a little bit, they will tend to grow in the vicinity of the uncontrolled, in the vicinity of an inner horizon. And well, that would possibly back react on the geometry, so the description that you are giving would not be complete, and then, well, that may lead to actually another singularity, either null or spatial singularity, okay? So what about this? So one possibility, which is perhaps if you want, a bit brute force possibility, but it solves the problem, I think, is to consider inner extremal black holes. So this is a bit weird in the sense that you are actually imposing that the surface gravity in the inner horizon is actually 0. So instead of having a blackening factor like the one I was showing you before, it would be something like this. So well, here the inner horizon has 0 surface gravity and then there's no mass inflation, okay? There's no problem with this. Actually, there's a funny way of doing this in 3 dimensions in a way that doesn't require any kind of fine-tuning. So I just point that there because, well, okay, it's actually remarkable. But well, some people show that these inner extremal black holes exist in our models. It's sort of trivial that they exist in our models. You just need to fine-tune a couple of couplings, and then you will impose that this happens, okay? And then there's no mass inflation. The problem is that, of course, this is not very nice in the sense that it's not generic, okay? Because this will not happen generically for all the models. It will just happen for some particular choices of couplings that you need to fine-tune across different curvature orders, okay? But it's possible, at least. Then there is the usual possibility that, well, these solutions that I've been telling you about, if you poke a little bit the inner horizon, then they would just be you should interpret them as transit states. So it's not a stable thing, so it will go to something else. And the usual claim is that they should go to form some spatial or null singularities, okay? Recently, some people have considered also semiclassical corrections on top of the usual classical corrections, for example, in the ORI model. And they claim that it's actually possible that there are other outcomes that make the inner horizon behave in a different way from what one would expect from the usual Israel and Poisson analysis. And one possibility is actually, so several groups have claimed, I only put one paper, but there are several papers that claim this, that actually what happens is that the inner horizon, because of semiclassical effects, it may tend to actually grow upwards, so it becomes bigger and bigger and bigger, and at some point it may actually reach the outer horizon. And well, then the end point might be something like some extremal regular black hole, or even, and this is actually the original Hayward idea, although in Hayward's model it was completely out of nowhere because there was no dynamics or anything, but some people have actually done calculations in which they actually consider a normalized stress tensor sourcing fluctuations in the vicinity of an inner horizon and see what happens. And they claim that, well, they mention these two possibilities. So either you may end up with a extremal regular black hole, like the one I showed you before, or actually the trap region disappears completely. So there were never horizons to begin with. Okay, so for some period of time you have a trap region, but it actually ends up disappearing completely. Okay. Well, anyway, so these are possibilities, and well, the good thing is that we can study them and we can actually do this kind of analysis. We are at this point trying to do some kind of starting to do some kind of ORI-like kind of analysis for classical perturbations, and then we would like to include also semi-classical perturbations and see what happens, okay, with this. So this is the first thing. Second thing is regarding going beyond spherical symmetry. So I did everything in the spherical symmetric sector. I told you there is a Birkhoff theorem, so the dynamics is very well under control in that case, but if you go beyond spherical symmetry, then it's not so clear what happens. So I think a very important consistency check of all this is to actually do gravitational perturbations beyond the spherical symmetry. Okay, so this is something we have started doing, and it looks a bit promising. It seems that for at least at the lower orders, the order of the equations remains second order. So it seems that well, it's possible that there are no problems with instabilities if you include perturbations that break spherical symmetry. Okay. And finally, there's another thing that should be mentioned, which is stability on other backgrounds. So these models that I'm presenting here, if one treats them non-perturbatively, as I'm doing, they introduce, in principle, they may introduce ghosts. Okay, this is the usual Ostrogradski theorem, which is not really a theorem in the context of field theory, but let's say that for non-degenerate Lagrangians and so on, more or less, it is correct. I should say, first of all, although, okay, I don't want to be very emphatic about that, but some people try to make sense of higher quadratic-gravities even in the presence of Ostrogradski instabilities. For example, Alberto Salvio tries to do this with quadratic gravities. So he says that the ghosts instabilities may be such that they are essentially irrelevant for example, I don't know, having a universe that expands and does all the things and so on. So you may have metastable configurations, and these instabilities are actually not relevant. Okay, even at the quantum level, where these things should introduce non-unitary effects. Okay, this is the usual problem with the quadratic gravity from Stelle and so on, where he found that you can make renormalizable instant gravity by adding quadratic terms, but it's at the price of making it non-unitary. Okay, so well, there are attempts of dealing with them. In any case, you can actually address this problem in a different way, and this is by doing something even more brutal than what I'm doing, which is including actually explicit non-local f of box terms in the action. In fact, this is something that people are doing these days to actually do evolution of higher quadratic gravities, like, for example, the group of Pau Figueras and others. The Ostrogradski theorem does not apply if you have, actually it's something else. I should say the Ostrogradski theorem does not apply if you have infinitely many derivatives. Okay, so that's one thing. So if you choose these terms carefully, you may actually avoid instabilities altogether. Okay, that's one thing. You have to be careful to add these terms in a way such that you do not destroy the regular black hole solutions that we have. And there's actually a way to do that. So you can have a theory which doesn't have instabilities. It's probably perturbatively supernormalizable around flat space, something like that, and it still has regular black holes. Okay, that's something that we're working on, but we'll publish it probably soon. Yeah, okay. So let me mention a few additional future directions. We would like to study evaporation. It's actually related to some of the things I said before, some of these perturbations and so on, like semiclassical ones in particular. What happens with critical collapse? In this case, there are no singularities, so what happens if you fine-tune the parameters so that they actually lead a naked singularity of zero size in these models? Another question. You can start study other things. Now you have a framework. You can study static stars. This framework is also remarkably tempting to think of using it for doing the microstate counting using the techniques developed by many of the people in the audience. Because, well, it has spherical symmetry, you have shells, you have a well-defined thermodynamic system that I haven't told you, but they do satisfy. So in principle, you can actually try to do the same kind of analysis. You can study other asymptotes. And there's something that I find interesting, which is perhaps that maybe there is some kind of classical string interpretation. I was looking at the literature, and perhaps some people know more about this. There's a paper by Perry and Tao that I just found yesterday, to be honest, where they claim that in the two-dimensional black hole in string theory, you can somehow quantify the effects of alpha prime corrections, and when you include the whole tower of corrections, actually the singularity is gone, so you get a regular black hole. I couldn't find any other examples in which this happens, in which you have an actual string theory model where you have the infinite tower of corrections in alpha prime and see what happens. So maybe this has some kind of classical string interpretation. And then, of course, especially for people, well, actually, this may be, in other audiences, this is the most important one. Perhaps maybe this audience is the less important one, that we care about 4 dimensions. But in 4 dimensions, it's trickier because these theories do not exist to begin with. So you have to do something else. And we have some ideas, but I will not comment on that because it's still preliminary. So that's it. Thank you for your attention.
Let's take a break. Okay, so we have plenty of time for questions.
The one that is not produced by gravitation collapse is two-sided again, and what has in the middle? What has in the middle? What is the Penrose diagram?
I don't have it. I cannot show it. But it's an eternal black hole with 2 sides. Exactly. Yes, it's similar to Schwarzschild. It has an inner. It's similar to Kerr. similar to Kerr, but there is no singularity. There's no time-like singularity.
So it never ends and goes to other universe.
Yes, yes. You would expect that this is just for the eternal case. I mean, if you add perturbation, something should happen to the inner horizon. That's clear, but yeah, that's something to be explored.
So was there meant to be a direct connection between this resummability and the Birkhoff's theorem that you can see without all this machinery in between?
No, not really. So you may suggest that these theories may satisfy a Birkhoff theorem because there's a reduction in the, so the equations simplify a lot in spherical symmetry. But actually, not all of them satisfy a Birkhoff theorem. There's actually a subset of them, and it's far from obvious that you may prove it like that. So it requires a lot of calculations actually to show that the Birkhoff theorem implies that they satisfy this. The other way around is simpler, but yeah, so it's not obvious.
So what is the string theory model for which Perry et al. Claimed that the singularity is gone?
What's the model?
Yeah, what are all these infinitely many corrections they claim to be taken into account?
Yeah, I cannot tell you much, but they mentioned that the parameter that plays the role of alpha prime, it's some Kac-Moody level that is supposed to, and they actually mention it. They say if you include, this is like including all the higher order terms, but there are no higher order terms in the paper. So honestly, I don't understand it. So.
Well, so you're restricting yourself to the terms, to the correction terms which are polynomial in the curvature. If you will allow something like square roots of r squared plus something else, that can probably give you an opportunity to have your result extended to 4 dimensions, I think.
You mean like covariant derivatives, or sorry? I didn't
No, it's if you just if you consider some curvature invariant and consider non-polynomial functions, but something else. Yeah, that should probably give you an answer in 4 dimensions, right?
You are absolutely right. That's actually the thing I didn't want to tell.
Okay.
You're absolutely, yeah, that's it. That's the solution actually.
Yeah, that's. Then let me explain why I am right.
So he's saying that if you include non-polynomial things in the Lagrangian, like for example things like square root of Weil square, for example, you can actually achieve this. But we don't like it so much in the sense that these are way less motivated than this in a sense. But you can do it, yes.
Yeah, I mean, so that's my guess was because then you reduce any Einstein gravity in any dimensions, or any gravity in any dimensions to 2 dimensions spherically symmetrically. You are getting to what is called dilaton gravity in 2D, and probably what you're calling Herondetsky gravity.
Yes.
And they have a lot of potentials.
But not all of them you can lift to actual theory. Not at all.
Yes, sure.
So only a few of them. Yeah. And the problem with 4 dimensions essentially boils down to a property of the Weil tensor. So there's a property that the Weil tensor square satisfies in 4 dimensions that trivializes it, and it doesn't satisfy it in higher dimensions. That's essentially the source of why it doesn't work in 4, unless you do exactly what you said.
Okay.
Then you can do it.
Thank you.
If you take a generic higher order theory and you do this field redefinition to go into this frame, you get this metric. If you would undo the field redefinition, would you expect to still have a metric that's qualitatively like this? Because it's conceivable that the field redefinition will produce the singularity again.
Well, no, right, no. If the field redefinition story that I told you, it's only true as long as the couplings are small. So if you go to this frame, as long as you remain perturbative in the coupling, so for example, we take the solution, you expand it like in alpha to leading order, then that's correct. But of course, that doesn't capture the singularity resolution. So that's the problem. So that's the thing, that's the catch. If you want in terms of, because otherwise I would be telling you that, okay, I'm resumming any effective action, but that's not true because I'm resumming a particular effective action. I'm just saying that this thing is general enough to be capturing all the perturbative terms, all any effective action at the perturbative level. So what you're saying cannot work because of that, because I don't know if I'm explaining myself.
But if you write down, the question is what an actual probe, what metric an actual probe sees. Like if you have a string, you see a different metric from a D-brane and so on. And if you start with the string effective action, say in some background, then that's the metric seen by the string, if you want, right?
Yes.
That's the, now, if you start to make this field tree definition, that's no longer the metric that the string sees. It's a metric
Yes.
that perhaps some other thing sees, but not the string. The question was, if you undo the field tree definition, so if you go to this frame, you compute, you get this de Sitter core, you map it back to the original variables, whether it will remain regular in the original variables, or whether in that field tree definition.
Right. No, I understood the question. I'm just saying that it wouldn't. Probably, because that's what I'm saying, that the regularity is a feature that is non-perturbative in the couplings.
Right.
So that what I'm saying about going back in the frames, it's only true perturbatively in the couplings, and I'm doing something beyond perturbative. So all the features that are at leading order in the couplings will remain unchanged in both frames. You can do it in one frame, or you can do it in the other. But the regularity aspect, is not the capture.
So it might still be singular in the original.
Exactly, in the other,
Any more questions? Oh,
Yeah.
Space, is there a seated space inside?
Yeah, it's like a de Sitter core. It's not the de Sitter space, but it looks like de Sitter. Yes. No, it's literally what I told you. Like at the level of the metric, it looks like 1 minus r squared over L squared. It's the usual, but it's not exactly de Sitter because there are other terms that appear. There are corrections to this that appear at actually even orders so that there is no singularity.
more questions?
So maybe I have one question. So when you integrate out this and construct this effective theory, in general, you would expect that these alphas would be positive and negative or whatever. But for you, it has to be positive, no?
No, not necessarily. It was just a sufficient condition. It is not necessary. You can put some of them to be negative. You just have to be careful on, if you put one which is very negative, for example, then this algebraic equation that I was showing you, may have, for example, a finite volume singularity, for example. So there are other zeros in the F, and then, there are some mild conditions you need to impose. So it's not absolutely generic. It doesn't work for any theory. You need some mild conditions to impose.
Okay, if there's no other questions, let's thank Pablo again.
Thank you.